I'll be presenting constraining astrophysical observation using gravitational wave background that we have received in PTA last year. So we know that gravitational wave in LEGO that has been talked in this talk for in this conference for some time. So what I'll be talking more about is the pulsar timing array. So we have LEGO, which is from 10 kilohertz to 10 hertz to 10 kilohertz frequency. So with a radius of the detector from 4 kilometers. So to get lower frequencies, you need the length of the detector to be higher. So the LISA is proposed to have like millions of kilometers, 2.5 million kilometers, I think, length with all the three things. So at that frequency, you can get much smaller frequencies. And to get even much more larger, we use pulses, which are like a kind of perfect clocks in the universe. So which we get thousands of light years as our detector length. And we get the frequency up to at nanohertz. So you can see pulsars are rapidly spinning, and we take only the millisecond pulses. In that, by calculating the time of arrival of that pulsar, we can calculate gravitational wave background from that. It is a bit complicated than LEGO because it has a lot of arrays in between from the interstellar medium, and each pulsar you have to consider its profile and all the differences. That's why it has been much more time. So the pulsar timing community is mainly there are three: the American one, European one, and the Australian one. Then there is the Indian, Chinese, the American, South African. These all are collectively part of the International Pulsar Timing Array community. And this is the IPTA paper which came this year. So which combine all the pulsars that the possible the evidence of the detection of the background. So they have used like about 68 pulsar in nanograph. A total about 80 pulsars has been. We take a correlation between 80 pulsar to get this background that I'll talk about. So you can see the top figure is the what we can say the background, and the second figure is the most important one because that says the correlation between the pulsar. So when we calculate the timing, we can get some profile. We plot it, we get something. But how do we know that's the gravitational wave or not? So for that, the second between we take the correlation and we have to understand the correlation. If it follows that dotted line, then that's the correlation for a profile of gravitational wave by supermassive black hole binaries. So if we have a monopole, then there will be a straight line correlation. So, and by different noises and or the red noise or correlated noise that have different kind of sinusoidal or some other kind of correlation. So you can see the correlation and separate that error. And so last year we had find mostly possible the gravitational wave background in PTS. So when we say gravitational wave background, because there are a lot of sources which are combining that, and what we detect is the sum of all the sources. And so there are even more models on that, which like we possibly say it's all from the galaxy mergers, which are the supermassive black hole mergers happening. But there are other models people are considering, like cosmological phase transition can provide gravitational wave, the theoretical models. So I'll just focus on the galaxy merger. the other new exotic new physics people are doing that to see. So what I'll consider is two possible detection. And you can see in the previous figure, we have from nanohertz to 10 raised to minus 7 hertz. We consider a bit below hertz because then we can see some sort of two different where I call lane is the profile going straight up and the other one is bending down. You can see the difference because it depends upon the profile of the supermassive black hole binaries. There can be, if it's, I'll say later, I'll show you that if it's too eccentric, the binary means the galaxy collision is too eccentric, then you can see the profile changing. One important thing I miss is when we say the galaxy collision, pulsar timing array doesn't take the collision. We can see the collision of these galaxies if happening in the Lisa range. What we see in pulsar timing array is their collision, they are in spiral space. So we can have a large distance between that. I'll say the time scale later. So we can see what I did is to model this in these parameters. So I'll say the parameters next. So if we use different functions to make the galaxy merger into take it to its flat. So we use the stellar galaxy stellar mass function to get the mass profile of the galaxies and pair fraction to get the differential pair fraction at a redshift for a certain mass at for the ratio in mass and the merger time scale, and we use black hole bulge mass relation. So what we see is like using this, these parameters can be constrained using the gravitational wave background that we get. So since we have a this is the merger rate. So merger rate, we integrate the previous merger rate with the ratio, then we get merger rate with respect to the critical mass and merger rate with respect to the redshift. And you can see the mass profile of the critical mass profile is much more merger happening at the lower end, means lower mass 10 raised to 5 times mass of the sun is much higher, but like we don't have to look for too much massive at the higher end. The lower end is contributing too much to the gravitational wave. And also you can see, if you see the redshift profile, if you see the really high redshift, it's not contributing that much to the profile, much more the lower redshift, like mostly our detection would be about 2 to 2.5, or that will be the range of the detection. And we can constrain the other parameters that I show, the galaxy stellar mass function and all, using this the detection we currently have. So the line and curve was the curve. So here that I say, like when I consider the lower end, I consider line and curve where the curve is happening. You can see the eccentricity. We have high eccentric galaxy mergers. Then we have this bending at lower frequencies than PDS. So there are other planned explorer which can get the lower frequency, but that's for far future. But just to see the profile, and that's the stellar density factor. And I use other cosmological simulation, large scale cosmological simulations like Eagle, Illustra, Simba, and all, to see whether this model and that simulations has the parameters we get that simulation are consistent, and we have received more consistent results using checking. Instead of talking more physics, I think I'll just go and say what the multi-messenger astronomy part of this we can more use, because as you can see, if we can find the more supermassive galaxies, like we have one, I think, of galaxy binaries we have detected with a few megaparsec differences, but we have a lot of different candidates for that. If we can detect in the X-ray or something, then we can profile it. We can calculate the gravitational wave theoretically and compare with the result and see is there a difference, or if everything is all we receive in the gravitational wave background is from only this, or we have some other additional non-physics that we don't know. In PDS, now we have the gravitational wave background, but we are trying to get individual sources of so individual binaries we can find, more strong sources we can find that. And when we have a strong source, since we have a lot of different pulsar, we can do much accurate mapping in sky profile with tens of square degrees, I think. So it'll be much easier to say at that location, but I don't think we can specify the redshift. So we have to look at each redshift, which is the suitable candidates. And then that will be one specific way to find supermassive black hole binaries, I think, or galaxy mergers. And if we updated our understanding method to find these black hole binaries, then it will be also useful for LISA, which the binaries will be much closer. And I think in this case, when we detect something, that will be there for years. But when LISA, we detect a supermassive black hole binary merger, we detect the merger phase. So it will mostly be for small period of times, maybe some years, but 10 days or something like that. So if we start now, we can do better using this. Thank you.